Yeah, thank you very much. And thank you everyone for coming out on a Friday, as non-standard as that is. So yeah, the title of this talk is Timeless Tech to Modern Magic, Building Multi-Agent Systems with Finite State Machines. I think it's clear to see which part of this title was generated by AI and which part was the best that I could come up with. So my name is Adam Turlson. I'm an engineer, not a marketer. So let's dive right in. What is a finite state machine, also called a state machine? Well, it's a model that defines a system's behavior as a series of states and the transitions between those states. So for an example, I've modeled here the game of rock, paper, scissors. So the state chart shown here essentially represents the rules and flow and behavior of the game itself. It's composed of many different parts. So the first being the state transitions, like how the game begins with locking eyes and moves on to selecting throw. It defines transition logic, the events that cause the states to transition from one to the next. Along with those transitions, you can model your actions and effects. So as it moves from one state into the next, you can have that model the side effects in your system. You can apply guards and conditions to those transitions to explicitly enforce rules for what is a valid transition in your system. And underpinning all of this, you can store contextual data that is used to define dynamic behavior in the state chart for modeling the flow. So one of the wonderful things about state charts is that they're completely, you can simulate them. So here I'm simulating the game and it begins with locking eyes. Here everyone can play. And then you say rock, paper, scissors, shoot. And then we compare our throws. Who won? I don't know. Best out of three? I've tried this 3 times and people don't play. Come on. Rock, paper, scissors, shoot. All right. Oh, I see lots of paper. One last time. Rock, paper, scissors, shoot. Ooh, that's so many scissors. Hold up your scissors. Look at all of those scissors. Okay, that was silly. All right, you compare your throws, and then the game is over in the transition there to the final state. So the other important thing to understand is then what is an actor? So an actor is a model of concurrent computation in which the actor is the basic building block. So this model provides autonomy and isolation. So you have independent entities or identities called actors, and they each have their own isolated state and behavior. And the actors interact with one another exclusively via message passing. And these messages are processed by the actor one at a time. So an actor can only do 3 things. It can send and receive messages, it can update its internal state as determined by its internal behavior and logic, and it can create new actors. And of course, an actor's behavior can be defined using a state machine. So all of the visualization that I'm showing in my presentation today was built using a library called XState. So this is a tool for state management and orchestration that allows you to model very complex application logic as state machines and actors. It has 0 dependencies, and it has about 30,000 stars on GitHub. So it's pretty well established. One of the cool things about XState is that it allows you to separate the what from the how, the description from the implementation. So on the left, you can see basically a configuration-like representation of a state chart. So you can see what context is available. You can see all of the available states that this can be in. You can see the events like on, run in the system and how that transitions the state machine. You can see here with the invoke actors that it is passing messages to and how it responds to the, or how it handles the response using guards and actions. And then on the right, well, on the left, you can see that all of that was represented essentially as strings. And then on the right, you can define what those strings actually do, or how they are actually implemented. So in this case, the exact implementation of the actor, the actions, and the guards. So what can you do with state machines and the actor model and a tool like XState? Well, I'll tell you what I did while I was at Best Buy from 2020 to 2022 in the retail transacting space. So the leadership had decided that they wanted to build a new way for customers to purchase products from their store. But the interesting part of that was that they wanted to do it not only without using BestBuy.com's checkout and cart system, but also to do it without their retail point of sale either. So we had the unique opportunity of essentially greenfielding a brand new transacting solution for Best Buy. So when faced with this challenge, how do you begin? Well, you begin with the data. So at Best Buy and at many other large retail corporations, the fact that a transaction has taken place is when a large multi-thousand line XML document is sent down a pipe. So there is a standards-based schema for what's called the retail sales pause log. And it captures who, what, where, when, and how that transaction took place. So from a domain-driven design perspective, I think it is accurate to say that this is both an aggregate root in that it encapsulates all of the business logic of everything underneath it, such as valid lines, and it is a source of truth. You know it is a source of truth because a Best Buy sales terminal, like a point of sale terminal in the store, will still be able to transact with you if it is disconnected from the internet, from the Best Buy corporate network, and from the rest of the internal store network, because it has cached all of the business rules that enforce the generation of a valid retail sales pause log. When that terminal comes back online later, it simply synchronizes or sends this pause log into a system called Sales Hub. And that system distributes that pause log to dozens of IT systems across Best Buy's landscape. And that produces probably millions of effects across the enterprise. So it does everything from updating the general ledger to sending out daily sales summaries. All of it is derived from these sales pause logs. So it's obviously, very central. So the challenge, of course, is how do you produce this sales pause log and ensure it is valid? It's not something that you can possibly create or accomplish within the life cycle of a single request, right? It's not like someone says checkout and then boom, okay, out comes the pause log. No, it's a process, right? It's something that takes place over time. So if only we had a tool that would help us model that process. Of course, we have it, it's called the state machine. So you can use the state machine for many things. What we used it for is called service orchestration. So in service orchestration, you have a centralized flow that is defined in advance by the state machine. So your sequence of states and how you transition between those states is known from the beginning. So here on the right, I've modeled really just a conceptual model of an end-to-end transaction journey that a customer might go through when purchasing a product from Best Buy. So contrast this with choreography, where you have a centralized hub, like a centralized event hub, and you have a pub sub model, right, where you're sending events into the hub. You could have one-to-many listeners that are responding to that event. In service orchestration, you have a centralized controlling node that is essentially directing traffic, what service gets invoked when a particular event occurs, and that's modeled using the state machine. So the primary advantage of this is that it is easy to implement what's called the saga pattern. So much like a database where you have a transaction where you want to make sure that all of your rows are either they all succeed or they all fail, right? Your transaction. Well, what if you wanted to implement something like that across multiple web requests? That's where the Saga pattern comes in. So it's a distributed transaction. So consider, for example, in the flow for self-checkout, after the customer has finished building their basket, they've added all of their items, they've selected their payment method, and we go on to authorize the payment. Let's say that's successful, but then when we issue the receipt, that fails for some reason. Maybe our receipt printer is not functioning or something. Well, we can't let the customer leave and believe that that transaction was successful, right? They can't leave without their receipt, and the business can't leave without our receipt, the pause log, right? So you implement this Saga pattern to say, okay, if the sending of the pause log or the sending of the receipt has failed, then I'm going to go back and apply what's called a compensating transaction. In this case, reversing that payment to get the customer back into a valid state where then maybe they could try again. So obviously, the state machine is very powerful in handling these kinds of edge case scenarios. It's all modeled in advance. It's all deterministic. There's nothing that can happen that is outside of this flow. And one of the wonderful things about this is that it's totally adaptable and modular. So we actually began in 2020 building an in-aisle transacting solution. So the blue shirt, using our application and backend services, could, on their mobile device, scan your products, use a Bluetooth attached card reader, collect payment, issue the receipt, and off you go. Well, what else happened in 2020, right? We started asking questions like, will anyone ever stand face-to-face with another human again? So we pivoted. Using this exact same workflow. We were able to modify just the authorizing payment step, where instead of using that Bluetooth attached card reader, we went to your .com profile and used the cards that you had associated with your Best Buy account instead. And that unlocked Best Buy's mobile self-checkout. So same workflow, except instead of the blue shirt driving it, it was the customer themselves. So this is actually available today. You can walk into a Best Buy, pull up the Best Buy mobile app, scan your own products, and walk out. You don't have to talk to anybody. Not that anyone knows that this is possible. Yeah.
Terrible yesterday. I was at Best Buy. No sales associates. Computers.
Well, we'll have to build an app for that too.
They got robots.
And I don't work for Best Buy anymore, by the way. So so the service that we built, we called the transaction orchestration service. And it basically did these 7 things. It creates sessions. So when you connect with your app, that creates an isolated, unique session for your journey. It takes commands like add item. It augments data with GraphQL, right? So we don't ask the customer to pass in all of the information that needs to be in the pause log. When they actually scan the product, they just give us the UPC, then we go out and augment that data with GraphQL. It orchestrates the requests via the state machine and the downstream service calls. It's sending events. There's a 2-directional socket between the transaction orchestration service and the mobile app. So you can send commands in and you're getting events back as things progress. It's storing context. So as this journey unfolds, we're storing all of the information that we need to generate the pause log. And then at the end, it's outputting that data model. What do these 7 things remind you of? Does it sound like any super hipster AI trends? I'll get there. So when I was getting this solution reviewed, with our security team at Best Buy. Bruce O'Dell, the senior principal security architect, said, and I quote, "I've never met a state machine I did not like." Now, it's a total appeal to authority to say, okay, well, therefore you should like state machines because Bruce O'Dell does. But why might someone whose title is senior principal security architect say that? And the answer is because of the significant advantages that state machines bring to the operator. They are predictable, they are traceable and auditable, they're reliable and recoverable. You can do what's called time travel. So you keep track of every event that happens, right? Those actors are passing messages, you log every single one of them. And if at any time you want to recalculate your current state, say you've lost it for some reason, you just load back that list of events and calculate what your current state is. If you only replay those events up to a certain point in time, you've effectively calculated what your state was at that time. And now you can create a new branch in history from there. So you can do really powerful things. They're low latency, they're totally declarative, it's easily tested. You can do model-based testing, so you can programmatically be certain that you're testing every valid transition in your system. They're modular and adaptable, like I mentioned. They're scalable, and you can handle those super complex error scenarios. Of course, they come with challenges too. You could have state explosion. Maybe you're trying to model a system that has thousands, millions, infinite states. It's probably not a good choice. You need to manage those transitions. What if an event lands in your system that is invalid for the state that your system is in? It doesn't do anything except maybe log that, so then you can fix whatever system is trying to perform an invalid transition. But it's something that you need to constantly be aware of. I mentioned that actors are essentially single-threaded. It processes a message one at a time. So how do you handle concurrency and parallelism? Well, that's where something like Azure Service Bus sessions and AWS SQS FIFO message groups comes in to help with that. There's a lack of flexibility. They're defined in advance. They're rigid, it's structured. Versioning, how does your system adapt when the state chart has essentially changed from one version to the next, and then you try and do something like time travel? Okay, how do you handle that? And there's certainly a learning curve associated with it. I think that learning curve is a joy, but you might be experiencing something else. So I want to bring your attention to that list of advantages and say that the wonderful thing here is that state machines are everything LLMs are not, right? State machines or LLMs are not predictable. They're not traceable. They're not reliable. They're not low latency. They're not declarative. They're not easily tested. All of these things. But the exciting part is that by combining these two technologies together, we can use the strengths of one to mitigate the weaknesses of the other. So fast forward to 2025, and no surprise, Gartner's #1 trend and everyone else is Agentic AI, where autonomous AI can plan and take action to achieve goals set by the user. But their #2 trend, I think, is just as, if not more important, and that is AI governance platforms. So these are technology solutions that enable organizations to manage the legal, ethical, and operational performance of their AI systems. Now, I'm pretty sure that state machines don't have anything to say about the legal and ethical piece here, but I'm certain they have something to offer to the operational performance of AI systems. So what are the requirements then of an AI agent? Well, they're autonomous, meaning that they can operate independently, make decisions, and take actions without constant human input. They're goal-oriented to achieve some objective. They're aware of context. they go out and get more information from their environment in order to make decisions. They can collaborate with other agents. They're integrated. They're interactive and responsive to humans and other agents. They have persistence, and they can adapt and learn over time. So now again, I draw your attention to this list. Does it sound familiar? I think there's connections here, right? We were creating sessions, right? Independent isolation. We were taking commands, going out and getting more information based on what was given to us, right? We're orchestrating requests across different systems. We're sending events back. It's communicating back to the user as status changes. It's storing its own internal context and using that to shape what happens next in the workflow. And at the end, we are outputting a structured data model, right? Just like structured output. So I think there's a lot of similarities here. What we didn't have is anything adaptive, right? It didn't learn and improve. And that is what LLMs can offer this picture. So then we have our building blocks of agentic systems. Our actors provide the autonomy and communication. State machines provide the structure and enforce the predictable behaviors in our system. And LLMs enable dynamic intelligence. So with that, let's jump to the agentic state machines pattern showcase. So here we get to see all of the beautiful state charts. And you know, I appreciate anyone who wants to give my repository a star, because those are the only internet points that I care about. So, and all these slides, thank you. All these slides will be available later as well. So I'll rush. I'm up to like 60 or something now, which is crazy, given the state of the code. So, all right, so the pattern showcase begins, much like the human race, with tool use. So why tool use? Well, tool use is really foundational, right? It gives the ability for the LLM to execute code outside of its own environment, right? But it doesn't do that directly. So when you're interacting with the LLM, it returns a JSON object that describes that tool call. It's up to you then, as the integrating piece of software, to figure out what to do next and to give that LLM the response to that tool call. So that sounds like a flow that you can model. So in this example, I have an agent that is writing a recipe. So now we could just use the LLM basically to say, give me a recipe for tacos, but I gave it a tool called get inventory. So it'll first check what ingredients it has available, and it'll create a recipe just using those ingredients. So this pattern allows us to expose additional functionality required by the LLM that allows it to improve its capability and response relevance. So right away, we can talk about human in the loop. So what if this tool call is super expensive or unreliable or risky? How do we introduce a human into this process? Well, the state machine is super modular and adaptable. So I've inserted a waiting on approval step. So here, we begin by calling the model, and if it's a tool call, we're going to wait on approval, and then we're going to listen for two events, either tool use denied or tool use approved. That first one was denied. It tries again. It got the approval to use the tool, brought the response back, and then it completed it. So the wonderful thing is that all of these components up here, using calling the model, using the tool, totally unaffected, right? Easily adaptable to introduce human inside this loop. Yeah. So the next pattern is feedback. So in feedback, instead of having one tool calling agent, you have two agents that are essentially working together. One agent is maybe producing the output, and another agent is giving it feedback on how it can improve. So you do this essentially because LLMs need time to think, right? It's rarely the case that a single call will get the answer perfect, especially in more complex scenarios, right away. So much like with humans, we get better when we have a chance to iterate over time, and that iteration dramatically improves with feedback. And that feedback could come from another agent or from humans. So in this example, again, the recipe writer agent from before is now put in partnership with a critic agent. So maybe this critic is saying how to make the recipe more healthy or something like that. So, you know, hey, try substituting sugar with honey, although I'm still not sure why that makes a difference. You know, you can model how many turns it has to improve. So in here, in this case, I'm looping twice before we accept the final result. So consider that because this architecture is composable, this critic agent is just an actor, right? So it's integrated with an actor, but that actor can again be another long-running workflow. The process to give feedback on that response could literally take months. It could run forever, technically, right? So it's a way of building incremental complexity like layers of an onion.
You go back to the slide.
Yeah.
So when I look at this, right, I understand you work with a state management system, so we're comparing agent to the state management system. But to me, an agent built around an LLM more looks like a classic workflow, right? It's a
Indeed.
workflow more than a state management system. There's a thin
I
line,
agree.
right? Okay, I have something that orchestrates stuff. I have various steps. I have tools involved. I have a third or fourth step. Another agent that critiques it. I compare more workflow than the state machine. What do you think?
Well, the state machine defines the workflow.
Sure.
So it's the same thing.
Yeah. I mean, oh, that's how we want to think about it.
Yeah, yeah. The state machine is a way of implementing a workflow.
Yeah, there's always a state, right, that's maintained, which is modified by each steps of the workflow, right? Yeah, sure. So there's always going to be a state. Yeah. Okay, go ahead.
Yep.
I just wanted this picture, like this was
Sure.
more like a workflow.
Yeah, no, it is a workflow. Yep, it's an agentic workflow. Yeah.
It's a question of why is the agent though? It's a state machine, sure, but was your question, are you calling these multiple agents?
No, I'm not saying. To me, like he said, like you can call an LLM and get a response, right? What does an agent do? To me, an agent is a workflow with LLMs right there.
Yes,
Right, so
100%.
Yeah.
Yep, totally agree. Yep. All right. So, okay. So next on our curve here is collaboration. So in collaboration, maybe you don't have just two agents, you have multiple agents now, you know, n number of agents. And in this case, you have multiple specialist agents that are working together on a broader goal, but each of those agents doesn't work on the entirety of that goal. They're just working on some small subset of the bigger picture, right? So you basically do this because of prompt scaling limitations, right? Like at some point you can say, okay, OpenAI, I want you to achieve this outcome and go through steps A, B, C, D, but eventually it's going to fall down, right? Like you can only push that lever so far. So once you've reached the limits of prompt engineering, what can you do? Well, one thing that you can do is start to compose smaller agents together into a broader picture, right? So it's not trying to just accomplish everything in one go. You break it down into smaller pieces and give that to multiple specialist agents, and then bring all of that together. So here our recipe writer has a team, and it's kind of like an end-to-end meal delivery pipeline. So we go from writing the recipe to maybe buying more ingredients. Ultimately, we're preparing the meal. Maybe we're getting feedback from the customer on how that meal was, publishing some sort of report, and then giving that report back to the original recipe writer to improve its recipe for the next customer. And just for fun, I showed that, again, these workflows can really last forever. There's nothing expensive here about having a process that in fact has no final state. So next, agentic orchestration. So recall in the transaction orchestration service that I talked about at Best Buy, we had a centralized planning node, right? A centralized service that was essentially receiving all of the events and deciding which requests were made next. Well, in agentic orchestration, that centralized planning is done by the LLM. And here, I've essentially registered all of the available next states. In this case, the planning agent has tools that say, I want to write the recipe, I want to prepare the meal, I want to procure the ingredients, I want to get feedback, and I want to publish a report, right? So all of those next states are essentially registered as tools to the centralized planner, and it can decide which state is next. Now, the list of available states is known in advance, but which one happens next is determined by the LLM. So you do this when your workflow is highly dynamic, variable, or maybe inconsistent. Basically, whenever you need reasoning by the LLM to know when a goal has been achieved or how to achieve that goal. And also, you only live once, so you may as well have some fun.
But dynamic orchestration wouldn't help in your Best Buy point of sale example, right? It wouldn't.
Probably not. Probably not. I mean, there might be ways to blend it, right? So like maybe they add an item and you want to use agentic orchestration to decide whether to offer a recommendation in that moment or something. You could kind of layer it in.
Ads. Yeah.
Ads?
What about coupons?
Sure.
Based on segmentation models.
Yeah.
Personas.
I mean, I think as long as you're blending deterministic with non-deterministic, that's probably good. You probably don't want to get into a place where your centralized funnel, like your core funnel, is beholden to the LLM to say, okay, now you can check out or something, right? Yeah. Okay, so in agentic orchestration, as we watch the flow here, you'll see that it's essentially jumping from the planning state into the next state. And then I've built guards that check which tool call came back from the LLM and then direct it to the appropriate state to handle that particular tool call. So you can see it kind of bouncing back and forth. And it accurately progresses through the state, and then we take it back at the end to the summarizing result and return the final output. So at this point, you might be asking, well, why not just use LangGraph, Crew AI, AutoGen, Pydantic, Finite? I mean, by the time this talk is over, there's probably 5 more options out there. And what I wanted to offer here is that I really believe artifacts should lead the way. So by artifacts, I mean code, I mean stories in your backlog, I mean test cases, designs, architecture diagrams, review feedback, anything that you can touch, share, see. And the wonderful thing about artifacts is that they really help set direction. They help build consensus. They help promote iteration over time. And ultimately, they help establish trust. So, and trust is even more important when you're dealing with the world of AI. So we return then to the humble state chart. So the state chart is a structured blueprint that defines the behavior and life cycle of an agent. It is standard, ubiquitous language to describe the behavior of that agent. It defines those state transitions, the state definitions, the transition logic, actions and effects, guards and conditions, and the contextual data. So we saw how, so standard ubiquitous language. Well, LLMs are good at language. How good are they at speaking in state charts? So for a bit of an exploration, I passed a screenshot of that state chart of the rock, paper, scissors game. And when I put these slides together, O1 was the latest and greatest. And I asked it questions about the state chart. I said, what is this for? It says it's a rock, it's a state machine or state machine or workflow diagram, to your point. Diagram for a rock, paper, scissors game. What comes after the shoot event occurs? Well, after shoot is triggered, if both players choose the same throw, the machine loops back. Otherwise, it proceeds to the comparing state. Well, when is it a winner decided? Well, you weren't specific enough. The round winner is decided in the comparing state, the final winner in the game over state. So it does a very good job at understanding state charts. Okay, that's step one. But the next question is, how good are LLMs at writing state charts? And that is the next step in this journey, agentic chartering.
One quick question, so if we go back to the previous state, I understand there's infinity authority in the elements of the state. How many states Best Buy has?
I can't answer that specifically.
Pages probably hypo hierarchical process.
Well, the self-checkout journey was, you know, a limited number of states that represents the customer's journey as a whole. Okay.
How many states?
Well, how many processes are you talking about, and how do you break those down?
Well, I have that I work with a big state definition of the factory. This is 1,000 pages of process.
Yeah. Surely there's going to be limits to this understanding. Yeah.
Comparison when you create this GPT with 200,000 pages. Comparison to it would be the same result.
Well, consider that this was accomplished with zero fine-tuning, right? The wonderful thing here is that it is understanding the standard ubiquitous language of modeling a system. And so you could potentially train it on relevant examples and even get better responses back than what was achieved with just this basic case.
My question was a simple example like this. That's confused me. So if you go from this simple input to ChatGPT to the real object, this is a state machine.
I now see the world as state machines. Everything's a state machine.
Apple created as a state machine. It's Apple. So what you can feed it to ChatGPT and ask it the same question.
But it's also not a state chart. So we're not referring specifically to the same thing. Yes, and any of those diagrams, I think, at least just based on this admittedly trivial example, gives you a good shot at using LLMs to derive insights into those state charts. If you were to invent your own like custom way of modeling that process that doesn't leverage the standard ubiquitous language of state charts, I don't think that you have the same.
Trivial example to the real, it's a big difference. From the trivial to real.
Well, I think real comes in many different shapes and sizes. And some of those sizes may work out of the box, and some may not. And some you may need to do more. Right. Yes. Break it down. Yep. And then you have collaboration to figure out the whole picture. So yeah, next step on the journey, agentic chartering. Can the LLMs actually write state charts for brand new novel processes? And honestly, I made up the word chartering. I think it's super apt. I think it's super cool. It like seems to fit perfectly, but I don't know in practice what this would really mean or look like. So if anyone knows of a better term for this that they've maybe found out in the wild, please let me know. Charter, yeah. So in chartering, as I said, that whole state chart can be created by the LLM. And why might you want to do this? Well, what if your goal is learned later, or it changes over the course of your workflow? Maybe the process that was kind of defined in advance is no longer sufficient, and we need a whole new set of valid transitions to proceed from where we are. You could generate a new definition of the state chart. Now, kind of an interesting thing about XState as I was playing with this, remember when I described the separation of the what from the how, right? That configuration-like object with a bunch of strings and the implementation details. Well, you could conceptually pass, or you could ask the LLM to generate that state chart config and still retain 100% control over all of the implementation details. So it can essentially just generate a JSON object that describes its hypothetical new process, and you can check that against available implementations or feed those implementations in up front to hopefully get a better response. So yeah, agentic chartering, that's, yeah. Yes. Well, when I was playing with it, I gave it kind of my situation of, hey, create a new process, use the library XState. So at least ChatGPT already understands XState, a little iffy on XState v5, but it understands that syntax of that configuration object that I mentioned. I gave it a list of valid events in my system and available actors, and asked it to create a new process. And it did an okay job. Definitely did not work out of the box. All right. So with that, and we're maybe running a little shy on time, I have my demo, red versus blue. So is anyone familiar with red versus blue from like a security testing perspective? Okay, so your blue team are like your internal operators, and the red team are the external threat actors. So the red team has the ability to launch and create new agents in the system. So for example, here's the recipe writer from before. And I'm trying to show, okay, what does the red team see in this journey versus what the blue team sees? So the red team says, give me a recipe for tacos. That was the initial prompt, and it gets a response back to make tacos, fill tortillas, blah, 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 blah. But on the operator side, you can see every step that it took to get there, right? Every single state transition, all of the messages that happen between them. So it goes from writing to using tool, it gets the available inventory, here's all of our inventory, and it finally returns the result. So, all right, let's play around with another one. So tool approval. So same thing as before, except this time we need approval. So it says, okay, the input, write a recipe for tacos. Customer says, please wait Well, I get approval, operator says, tool use approval required, send approve or deny. So obviously I'm gonna deny. So it says, okay, bring it back. Oh, okay, I'm unable to write a recipe without knowing the ingredients. And it returns a result back. It's actually interesting. Probably 90% of the time it tries again. So let's try it again manually. We'll launch it. And it'll ask for approval. So this time we'll approve. It'll get the response. Got approval. There it is. There's our recipe. Great. All right, let's do one more. So let's do chat. So in chat, I've basically hosted this agent as more of like a chatbot, right? So same capabilities as before, except now its initial state is idle and it's waiting for a message from the customer in order to set its goal. So I could say, just as I did before, give me a recipe for tacos. Writing, tool use approval, send approve. Got approval. Okay, to make tacos, do that. And this time I'll say, build a house. Build a house, stack bricks in a desired structure. Well, how did it come up with bricks? So let's go into our log here and say, scroll over in our available ingredients, there's bricks. So bricks was an available ingredient and it used that to make the house. Okay, good job. So this is called red versus blue. So one of the, okay, actually, I'm sorry, I'm not gonna show that because I'm gonna show a different thing. Okay, so that was red versus blue. And you can check that out. It's in the Agentic State Machines pattern showcase library. Okay, so you've seen me talk about XState. If you're building with agents, I'm happy to say don't use XState because there is a far better tool that I discovered maybe 2 months ago now called Temporal. So Temporal basically does all the crap that we had to do at Best Buy manually in terms of saving all of those events, handling retry, replay logic, calculating state, all of the observability, all of the hosting, the management, all of that, Temporal will do out of the box, and it's open source and free if you self-host it. It is the perfect tool. It is foundational for building robust agentic systems. So the wonderful thing about Temporal is that it has nothing to do with AI. This came out in 2019. It is a workflow engine. It allows you to write durable, event-sourced state machines as code using programming syntax in any language that looks like synchronous code, but is not behind the scenes. And I'll show you how that works. It gives you workflows that are, quote, guaranteed to run to completion. So there's a really cool demo on YouTube of one of their solution architects. He executes a workflow, goes steps A, B, C, and D blows up. So he looks at the code, and step D says, throw an exception to do. Okay, so the step in the workflow that was executed hadn't been implemented yet. So he opens up his editor, he implements it there, he commits that, performs a deployment, pushes it out into production, and the workflow picks up exactly where it left off and runs to completion. It's the perfect kind of durability that you need for the unexpected world of AI results, right? So here's the architecture of Temporal. You have your user-hosted processes. So you have complete control over your application, the Temporal client, and the workers. So the things that are basically processing the workflows and the activities. The Temporal side of this manages essentially the history of all of those messages and the plumbing for which worker receives which message. That's basically it. And then they put a fancy front end on it, which I'll show you in a second, which gives you total visibility, right? So you're essentially listening on this wire of all of those messages, every single event in the system, and you can trace everything, right? You call an LLM, what were its inputs? What response did it give you? You can do that. And you can do that at scale, right? So it's super exciting, obviously. I'm getting worked up just thinking about it. So how do you build agents or workflows with temporal? Well, rather than that configuration object with XState, it's all just built as code. And the critical thing that makes it an agent, while true. It's a long-lived process, right? It could run forever. While true is in your code. It looks synchronous, but it's not. It's not because here they're proxying the activities, right? So in your code, it looks like you're just invoking a function, but behind the scenes, it's hitting their proxy and they're converting that into a message that they pass to the actor, which then gets passed back as the result as a message, right? So that's how they're able to do all of these guarantees because they've.
Theoretical question. What is electrical failure?
What is what? Sorry.
Electrical failures happen sometimes. Nothing works forever. It's still I understand that sometimes you're not
Sure.
You can say that it's going to stay.
Because it's all.
Failure of the system.
Well, because you have every single event saved into the database. And so to recalculate your current state, you could if you didn't have snapshotting, actually you would save snapshots of every state so that you don't have to do this. But even if you didn't have snapshots, you can replay those events to recalculate your current state before processing that next message. It's event sourcing.
So this is much more efficient than traditional backup and database system. They enable this.
Well, I think maybe it's important to differentiate between like the kinds of data that you would save in like your relational store.
It's a simple example. It's possible. If you have thousands of
Well, this is used by very large companies at very large scale. So, I'll let you look at the banners on their website, but this is 1950s technology applied today on the cloud. It's tried and true, I would say.
It's still unsolved. Nobody can solve this problem with the database space. So if you have database or cloud, you don't need to backup of the database in the case of failure.
Perhaps. I think there's a difference between business objects that you would store in a relational database and logging messages and calculating workflow states. I don't agree to that. You would implement a state machine using the data in the database, perhaps to inform via context how your process proceeds or in which state you are, but the database itself, sure, the services under it might be a state machine, but I don't think that's what we're talking about.
So that's my problem.
Yeah.
So I just recently learned about LangGraph. Is your thought with temporal?
Don't use it, use temporal. LangGraph is dead. Yeah.
So it's like the same thing.
Yes, yes. And in fact, my own journey was learning LangGraph. LangGraph was my last stop before I got off and was like, I feel like I've done this before, right? I've done this using XState. And so that's how I got into XState and started exploring that. It's like, hey, I can build the exact same things using XState, right? Like, I don't need to use LangGraph. But now temporal's the way.
If you use LangGraph, you get the workflow, you get short-term persistence
Yep.
and long-term persistence, like database or
Yep.
you get the ability to tool call. You get the ability to use instead of
How do you integrate that workflow with your traditional software?
How do I integrate?
How do you combine your typical business process that doesn't have anything to do with LLM, that is touching all of your traditional
I can
services
expose that
with,
land graph stuff via endpoints and all those.
Yep.
So that's how I work. Like
Yep.
now, if I had a traditional piece of software doing whatever, and I want some input into that, I'd expose it via endpoints.
let me show you something that, well, I shouldn't say that because they have LangGraph Studio, which is
Right.
akin.
The
So
banks and
everything
the
is
bank-
possible, but if you're trying to solve these sorts of workflow challenges in a general sense, would you rather use a general tool that is foundational, that's built using 1950s technology, tried and true, or would you rather introduce LangGraph and Python and
To honestly answer your question, I said someone was building a framework, incorporate that in their technology, and use the framework in front of the end user. If I was
Yeah,
building
indeed.
LangGraph,
Yep.
yes, I would incorporate this kind of library to do my state, right? So
Sure.
the difference is whether I'm building an end state agent for my business, or if I'm writing LangGraph or Google ADK or whatever, right?
Right.
That's
Right.
how I see it.
Well, consider the ergonomics of this code, right? So this looks like very typical synchronous TypeScript. The only bit of temporal that you see is up here. Compare that with the ergonomics and developer experience and syntax of LangGraph. It's all LangGraph specific, right?
Because it's a
LangGraph is
framework.
also Python. This is polyglot. You can use any language, right? The generalized nature of something like temporal, I think, is a much stronger foundation than something like LangGraph. But no doubt you can achieve anything in either way. So that was the workflow. So key to note is that here there are no side effects. So this is basically an as code representation of the state chart. And so you want to avoid any possibility of an error happening in your workflow. So the fun thing is that temporal does some things behind the scenes to make this true. So for example, they block the use of promises. So they actually, in the runtime, will blow up if you try and use like the node promise API. They also block like math.random. I found that out when I tried to generate a GUID in my workflow, and it blew up because the crypto library was using math.random. So it's blocking any potential side effects in theory in this code. So where do those go? Well, they're in your activities. So these are functions behind promises. And in this case, my activities are, I didn't say that here, the activities like list tools, LLM chat is going out to OpenAI, call tool, these are interacting with an MCP client, which are, these are interacting with an MCP client, which is injected into the activity. So here you have a factory function where you can pass in all of your reusable clients to like talk to a database or talk to a MCP or whatever you want. And then you just write your basic promise returning functions here. And this is the atomic step in that workflow, right? The cool thing is like consider combining MCP and temporal workflows, right? Your tool call can itself be another temporal workflow. So you have durable MCP. So of course, because this is based on state machines in the actor model, there's really impressive developer tooling that allows you to monitor the progress of all of these workflows and activities. Obviously can't show all of it here, but you can see every step. You can click into those steps, see inputs and outputs of every step. It's all totally observable. And then when it fails, you get like red here, you go and fix something, it auto retries and continues on. So I returned to our charts and I asked, where is this arrow headed? Where are we going with all this? And I think the answer is toward emergence. So maybe if we're able to achieve that, we could finally understand what DevOps means. But I believe that if we are going to achieve something that performs, feels, and operates like emergence, it's not going to be because we're building agentic architectures modeled after the human brain. It'll be because we found a way to make building these systems feel like building with Legos. In my experience, all of the best technology today has that attribute in common, right? Whether you're building UI with React, you're building programs with functions, right? You're deploying your cloud infrastructure on AWS using infrastructure as code, right? In all of these cases, you have a reusable component that is composed into a broader system that is greater than the sum of its parts. So perhaps with that, the humble state machine may have a foundational role to play for the next 70 years as well. So thank you very much. Now we got some questions along the way, but any more? Yeah. Yeah. Like millions of workflows. Yes.
So,
Certainly. Yeah. Yeah. No, like just anything that you can model as an event in your system, you could introduce a human in the loop, right? So the mechanism that temporal would use for that is especially, I'm sorry, I skipped these, signals. So signals are essentially event handlers in the body of your workflow, where you can listen for that event coming in, right? So when this event occurs, how do I need to update the state of my workflow, right? So maybe I only listen to that before I hit the while true. Maybe I'm always listening to it. You know, how do you model that listener? You can do that using signals. There's also updates. So updates are like signals, except you have the opportunity to give a, I'm sorry, signals update the workflow state and there's no response. Updates can do the same thing, but they're blocking for the client. So you can give a response back. And queries allow you to just return some piece of your workflow state, no updates. So this is how you could introduce human in the loop, right? So if you wanted to wait after you get this tool call back, you could just, you know, pause there, wait for a signal, and then continue on. I'm sorry, can you repeat that for me? A use case for how temporal works? All right, let me tell you what I'm working on right now. So I'm working on a project for like a transportation logistics company. And long story short, part of their workflow today is to log into dozens of different websites and check inventory levels of products at hundreds of different stores. Rather than that, I have a temporal workflow which simultaneously will log into all of them, go and scrape all of the unstructured data, parse it into structured data, and then come back with all of those responses and jam them together into a unified data model in our database so that then we can build a dashboard and additional tooling around it. That whole process is managed by temporal.
Basically answers my question, but I just want to hear
Would you consider this like a replacement for data engineering orchestration as well?
Ooh.
Or not? 'Cause
I don't know
think
if I can answer that. What do you mean data engineering orchestration?
like Airflow or Dexter or
I've not used any of those, so I can't say. Can anyone else say? Does anyone else know?
yeah, because I mean, data engineering is based on the DAG, but you could probably define a state machine in a single direction. Because I mean, that was basically a data engineering task that you just described.
I hope you got your answer. Let's go have some beers and you can teach me.
As a programmer, I just look at the await LLM chart, and I just imagine as a data computer scientist immediately how many processes in my little application sitting here, when you get in this Best Buy and giving me advice which camera I want to computer, it's 100 of await states. Because then behind the signal for me is kind of, is it TCP? Is it web HTTP communication? What kind of protocols you use it? ISO 7 or whatever. So there's a little one statement in your code. Await.
Yep.
Behind it, it will be the whole world.
Anything asynchronous.
But it's technically it's again thousands and thousands of pages of code depending on is it AWS or it's in my phone, in a computer, in the system, in Best Buy. Because await signals is what you say, it's very simple. But then behind it, where does the symbol come from? What protocols you use?
Yeah, and in this case, it's MCP. In this case, it's MCP, right? So you're talking to
I created my agent.
standard
I
IO.
communicate with your agent and with other many agents like Best Buy, Target, or whatever, Amazon. And I want to do simple thing. I want to find where is this camera I'm looking for or monitor is best deal for me right now because I'm a consumer and you represent business. So I will talk to your agent at Best Buy in a Target and I will use the protocols to interact between my agent and all these guys Target, Best Buy, you will have something like a way that imagine how many protocols integration will be behind the scene. I think that is the real thing.
That is the protocol that's being developed just for agentic AI being talked to each other. I don't remember that.
You mean MCP? A2A as well? I haven't investigated A2A yet. I understand it's compatible with MCP.
Oh yeah, they're collaborating. Meanwhile, there are nodes
Wonderful, wonderful.
All right. Well, I think I think a lot of this can be discussed over beers.
That sounds like the way to go.
There you go.
Thank you very much, everybody.
Thank you.